working with my partner Andrew Watson, and we looked at the F-35 fighter jet afterburner operation time. So the turbine inlet is the hottest part of a jet engine, especially when a pilot needs to use the afterburners. For a rapid acceleration or supersonic flight, afterburners provides a significant increase of thrust, but causes significant temperature increases. This can specifically be seen on the F-35 fighter jet. Its jet engines afterburners provide significant thrust, but higher heat growth as a result of the afterburners being turned on. Engineers need to know how long the material in the turbine will take to reach its maximum allowed temperature. And the approach we took to solve this problem is by using the heat equation. We used the partial differential equation to figure out how much time it takes for the turbine to reach its maximum temperature when the afterburners are used. Thus, we know how long a pilot can operate the afterburners before the material reaches its melting point. Some assumptions that we did. Um, so the F-35 jet engine turbine inlet is made of Inconel alloy 718. It has a special ceramic coating. This material is high strength, but it's a good creep resistant. It has good creep resistance for higher temperatures. The coating properties of the Inconel alloy are classified. So we are assuming that this alloy has no coating since we don't know the properties of the coating. And Inconel alloy is homogeneous and isotropic, which means the thermal properties are uniform throughout. We also assumed this problem to be one-dimensional since the temperature changes only in the y direction, as you will see in the schematic in the next slide. It is also assumed that conduction is the main heat transfer at this location. We also assume there's going to be constant density, specific heat, and thermal conductivity. And this problem is for a semi-infinite solid with a sudden change in surface temperature.
So to figure out these calculations, we started with the boundary conditions with the normal operating temperature of the turbine inlet surface temperature to be 1,473 degrees Kelvin, and the turbine inlet surface temperature with the afterburners on raises up to 2,260 degrees Kelvin. So you can see that we have our thermal conductivity, density, specific heat of the Inconel alloy 718. And then we have listed the melting point as well is 1,609 degrees Kelvin. Next slide. So we started out with our heat equation, and through transforming it through the similarity solutions, we were able to get an ODE that we then used, as you can see, the Ty of T minus T naught divided by the T surface temp minus T naught equals the air function Y divided by the 2 square root of CT, and C is the thermal diffusivity. And so through those calculations, we plugged in Ty of T would be the 1,609 degrees Kelvin, which is the melting temperature of Inconel, because we want to figure out at what time that will reach that melting temperature. And then T naught is the normal operating temperature, and then TS was the surface temperature when the afterburners were applied. But through plugging all those variables in and calculating it, we were able to find that the time the max operating time before we hit the melting point in Inconel would be 328 seconds. And then when we added a safety factor of 1.5, that brought it down to the T equals 219 seconds, which is 3 minutes and 39 seconds is our max recommended time to operate the afterburners. Next. And then here we have our references listed that we were able to get our sources of the Inconel 718 properties, as well as the second source is where we got our information for the F-135 engine and operating parameters.